Welcome back, everyone. In today's lesson, I'm going to talk to you about the concept of the mole, which is a unit of measurement to express reactants and products in chemical reactions in a convenient way. The mole is a unit of counting, and it refers to this link between the macroscopic and the microscopic world. We need to know about this number here, 6.022 times 10 to the 23rd, which is known as Avogadro's number. This number represents the number of atoms that are in 1 mole of any substance. So this could be an atom, it could be a molecule, or it could be a compound. Or it could be even something like an object, like an apple. Now this number is a very vast number, and it helps us because a lot of times when we're dealing with atoms, we're dealing with them on the macroscopic scale. So in the laboratory setting, we'll be weighing out our chemicals on a chemical balance. And when we do this, we can't actually individually count the atoms. But we get a mass, and I'll show you in a minute how we can relate a mass to the number of atoms in a molecule or in a compound. All right, so this number here is Avogadro's number, and it represents the number of atoms in exactly 12 grams of carbon-12. This is a standard definition. It's changed since 2017, but this is very close to still being correct. This is the number of atoms that we refer to as 1 mole. And it's just from this information alone, we can actually determine some interesting things. Like, what is the mass of a single carbon-12 atom? Well, if we know that there are 6.022 times 10 to the 23rd atoms in 12 grams of this isotope, we could just take that amount of mass and divide it by the number to find the mass per atom. So let's kind of do it like this. If we have 12 grams of carbon-12 and we divide it by 6.022 times 10 to the 23rd atoms of carbon-12, what we'll end up getting is that the mass of a single atom of carbon-12 is 1.993 times 10 to the negative 23rd grams. That's a really, really small mass. We can also determine what the mass of a single AMU is. So if you remember from one of our previous lessons, when I introduced the concept of the AMU, I think it was in lesson 3 or 4, I said that the AMU, the atomic mass unit, which is how we compare the relative atomic masses of the different atoms and isotopes, is equal to 1/12 of the carbon-12 mass. Well, we have it right here, right? So it's going to be 1/12 of this. So 1 AMU is 1.661 times 10 to the negative 24 grams, or equivalently 1.661 times 10 to the negative 27 kilograms. And we'll see this one cited in our textbook. And we can use this anytime we have an atomic weight on our periodic table to figure out what the mass of any atom is now. So say, for example, we're looking at the element zinc, which has a atomic mass of 65.38 AMUs. 65.38 AMUs. I forgot already what it was. 65.38. Then therefore, it's going to have a mass that its atom would have a mass of 65.38 times this number. Okay, so the mass of a zinc atom is 1.086 times 10 to the negative 25th kilograms. And to say this more correctly, this would be an average isotope of zinc, because there's a variety of different zinc isotopes. So this would be an average atomic mass. So that's an interesting thing that we can do now, now that we know the link between the macroscopic and the microscopic world. Now there's something that will be a little bit more helpful for us to note, is that the mass of 1 mole of atoms of an element is can be referred to as the molar mass. So we don't usually want to know about the mass of a single atom, but the mass of a mole of those atoms. And conveniently, this is the same number that's the relative atomic mass of that element. So when we look at the periodic table and we look at zinc, 65.38 AMUs, that is also the amount of grams there are in 1 mole of a zinc sample. So when I look, let's look at helium for instance. 1 mole of helium is going to weigh 4.0026 grams per mole. So 1 mole has a mass of 4.0026 grams. When we look at phosphorus, it has a average atomic mass of 30.97 AMUs, but that can also be said that it's 30.97 grams per mole. 1 mole of uranium. Uranium is mostly the 238 isotope, so it's close. So it's 238. So 1 mole of uranium would weigh 238.03 grams. So much heavier than phosphorus and much, much heavier than helium. Nitrogen is N2. So in this case, we can actually figure out the atomic, the molar mass of the molecule. So what we need to first do is take the average atomic mass of the element, which is 14.007, and multiply it by 2. And then that's all we need to do here. .014. And we can do that for a compound as well. So if I have barium, and then this is referred to as thiocyanate. So if I have 1 mole of barium thiocyanate, I can add together the average atomic masses of each of these different elements, in their appropriate amounts, and then I can find how many grams per mole that is. So if I have barium that is on the left side of my periodic table, 137. Let me look at how I formatted it in my notes. Yes. Okay. So 1 barium equals 137.33 grams. 2 sulfurs, because this now this subscript is going to be referring to all those elements that are in those parentheses. We haven't done too much with parentheses yet, but this 2 applies to each of those elements. So we have 2 sulfurs, we have 2 carbons, and we have 2 nitrogens in this formula. All right, so sulfur is going to be over here. So we have 2 times 32.06. We have 2 carbons. Now, carbon 12 is 12.00, but carbon, the average atomic mass of carbon includes some carbon 11. So that's why this is slightly over 12.00. And then the nitrogen here is 12.14.007. It's good practice to use all the numbers that are on our periodic table so that we don't introduce any rounding errors. All right, so when we add this all together, we should get 253.5. All right, so that's how many grams there are in 1 mole of barium thiocyanate. When we look at a comparison of a lot of different compounds, this is how 1 mole of each of these compounds would look. On the far left, we have elemental sulfur. We have a jar of sucrose, and sucrose is a molecule composed of carbon, hydrogen, and oxygen. And so there's quite a few carbons, hydrogens, and oxygens. So this actually becomes the heaviest and the biggest jar. We have copper sulfate pentahydrate, sodium chloride, copper, which are these little spheres here, and then this red powder is mercuric oxide. And you can see that they all have different masses, and that's because every atom has a different mass. Now that we understand this concept, we can kind of use this to help us carry out chemical calculations. And to start off with, we need to know how to convert between grams and moles. And when we talk about moles, you got to think about this as a counting unit. It's the amount of a substance. This is an SI unit. When substances are going to react, they're always going to do so in simple ratios of moles. And that's why in the last lesson we talked about how to balance chemical reactions, is because we want to know, we want to make sure that these substances are reacting in simple ratios. When we measure substances, we have to do it in grams. So before we can compare any two substances, we're always going to need to convert them into moles. And this is something that you're going to have have to get used to. We can't compare the masses of two compounds directly, like we were doing in lesson, I believe it was 3. We were doing this in lesson 3 and 4. But now we can't do that because we want to actually compare them in terms of whole numbers. So to convert between grams and moles, all we need to do is divide through by the molar mass of a compound. And I can show you this using dimensional analysis. So say, for example, we have methane gas. If I have 32 grams of methane, and methane, to remind you, is CH4. If I divide through by the molar mass, which is the same as multiplying by the reciprocal, so multiply by 16 and the molar mass of methane we have to calculate. So 1 carbon is, so how do I know what the molar mass is? I got to show you that. So so we have, I always want to jump to it, I'm so sorry. is 1 carbon, which is 12.01, and 4 hydrogens, which are 4 times 1.008. And then when we add these together, we'll get the molar mass of methane. Which is 16.042. And we can truncate the last one because of sig fig rules. Remember, when we add numbers, we truncate it at the value that has the least number of decimal points. But I'm going to go ahead and leave it in here for now. So 16.042. And this is the amount of grams per 1 mole of methane. So this is how many grams of methane there are per 1 mole of methane. And when we divide these two numbers, we're going to get how many moles of methane that we have. On this one, it should come out to a pretty even number. Okay, it's just about 1.995 moles of methane. And we can see when we use dimensional analysis, grams of methane cancel out, and we're left with moles of methane. On your homework problems, you're going to be doing a lot of this dimensional analysis. Now, if we want to go the reverse direction, we want to calculate the amount of mass that we have from the amount of substance. We can simply multiply through by the molar mass. So let's say in this example we have 3.000 moles of carbon dioxide. All right, so carbon dioxide is CO2. Well, we need to know what the molar mass of CO2 is. So let's calculate that. It's 1 carbon and it's 2 oxygens. So carbon is 12.01. Oxygen is 15.999. I always just round it to 16.00. Okay, so that's like times 2. So 16 times 2 is 32, plus another 12 gives us 44.01. And when we multiply here, this is the amount of grams there are of carbon dioxide per mole. And that would mean we have 132.03 grams of it. Just showing you that cancels out again. And that's the simplest thing we need to know how to do. We need to go from grams to moles and moles to grams. All right. Now, we can also determine how many atoms we have, and I showed you kind of how to do that above. And if we have the moles, and we want to calculate how many atoms there are, say for example of aluminum, we just multiply through by Avogadro's number. Because Avogadro's number is the amount of atoms there are per mole. So if we do that for each of these, we'll get the same number for all of them. So this times 6.022 times 10 to the 23rd, that's 6.022 times 10 to the 21st. Now we don't need to do we don't need to only do this with atoms. We could do it with molecules. So if we have 0.01 moles of oxygen, we just multiply by Avogadro's number again. And then if we have a compound that's made up of a metal and a non-metal, we could call this formula a formula unit. That's the kind of standard name for it. A formula units of CaF2, so we can do the same thing with that. The generic name for all of these are entities. So atom, molecule, formula units, ions, objects, apples, they're all referred to as entities. So that's what this means. And then if we want to go from entities to moles, we just divide through by Avogadro's number, because Avogadro's number, again, is the amount of atoms there are per mole. So if we do that in this one, let's see what we get. Okay, so this is roughly 8.52 moles of germanium. All right. So anytime we're doing a chemical reaction, if you end up with a large amount of moles, like greater than 1, just make sure that you are doing the math correctly. We typically work with amounts in the 0.1 to 1 mole ratio. Or sorry, 0.1 to 1 mole range. But sometimes we work with large amounts, especially in industrial chemistry. All right, so let's get into the actual stoichiometry part. This term, stoichiometry, literally means to measure the elements. Stoichion means element in Greek, and metry is to measure, so measuring the elements. And when we have a balanced chemical equation and we have a starting amount in either moles or in grams, we can calculate the theoretical amount of material that we're going to get as a product. There are other things we can do other than just calculating how much product is produced in a chemical reaction. We could also work backwards and figure out how much substrate is needed to produce a certain amount of product. We could also figure out how much excess reagent is going to remain at the end of a reaction. And all of these things are starting points for any further chemistry that we're going to learn. So this is why I'm introducing this in the beginning of this class, because I want you to really know how to do this by the end of the semester. So we'll be seeing this a lot. Now, the most simple calculations are finding out how many moles of product or how many moles of substrate you're going to have given the other. This is always a one-step calculation. And then if we want to keep going, we can say, hey, what if we have grams of a reactant and we want to find the moles of product? That's two calculations. And that's what I mean by 2 steps. And then we could also go from grams to grams, and that's going to be 3 calculations. This last one is going to be the most common you'll do in chemistry classes. So this flowchart here that I have, let me move these down here. Give me a second. Okay, so I cleaned that up a little bit. But yeah, here is a flowchart that will help you through the rest of the semester. Feel free to print one of these off. It's under the handouts on our modules page. And it shows you the steps that are needed to go from any amount in mass, particles, or volume, or even a pressure or temperature of a gas to a different compound. So let me show you how this works. You're going to start with some starting material, and then you'll have a target compound. So your starting material is A, and your target compound is B. Now, A doesn't necessarily need to be a reactant. A could be a product. So this doesn't necessarily have to be something on the left side of the equation. It could be on the right side of the equation. So A is just whatever you're starting with, and B is wherever you're going to. And this will tell you what what operation you need to use. So if we're going from grams to moles of that starting material, we just divide through by the molar mass of it. You may need to calculate the molar mass. Usually that's a starting point for any one of these calculations. Once you've done that, you want to calculate the number of moles of your target compound. You use the balanced equation to do this. And after you've calculated the moles of that target compound, then you can calculate any of these other properties, depending on if it's a solution or a solid or aqueous solution. But the balanced equation will need to be where you're essentially multiplying through here on the top by the moles of B, and then on the bottom you are, I guess like the way I'd kind of write it is, we have B on top and A on bottom. So the coefficient of B on the top and then the coefficient of A on the bottom. I'll show you what that means in just a sec. So let's go through and practice these problems together. And when we get about halfway, I think you can probably pause the video and try them on your own. But all this is going to be found in the supplemental chapter for our textbook. You can also find it in chapter 11, but the supplemental chapter kind of breaks it down a lot simpler. So let's start with this reaction here. I have nitrogen reacting with hydrogen to form ammonia. This is the Haber process. We'll talk about this later on this semester. But I want to know how much ammonia, which is NH3, can be produced from 2 moles of nitrogen. So if you looked at this, you might think the answer is just 2, but we need to balance the reaction first. None of them that I'm going to give you to begin with here are balanced, so we need to practice this. Well, the nitrogens here could be balanced first. If we do so, we can put a 2 here. And then we want to balance the number of hydrogens. Well, we need to have a total of 6 on both sides, so we can put a 3 here. All right, now that we have a balanced equation, let's start with 2 moles of nitrogen. So I'm going to use dimensional analysis for all of these problems. So my abbreviation for moles is MOL, or MOLS, so 2 mole or 2 moles of N2. And I'm going to use the balanced equation here to help us figure out how many moles of ammonia can be produced. So all we need to do is look at the coefficients, and I'm going to add a 1 here just so we can see where this comes from. Well, there's 1 mole of N2, and for every 1 mole of N2, we can produce up to 2 moles of NH3. All right, and that's pretty useful. The reason why this works, and it looks like we're doubling our starting material, is because the nitrogen changes forms. So we have 1 mole of these nitrogen molecules, and they kind of recombine with these hydrogens in a way that gives us 2 molecules. So we didn't actually lose any nitrogens in the process. So 2 moles of NH3. Right. And so if you set this up, we have our moles of B on top and our moles of A on the bottom. And there we go. We end up with our target. All right, in this next example, I have hydrogen and oxygen combining to form water. So we need to balance this one. We could use a fraction, or we could just simply multiply this through by 2, and then change the number of hydrogens. Okay, so let's go and do it this way. How many moles of water are produced when we have 5 moles of oxygen used? So we need to understand what's being asked. We're starting with 5 moles of oxygen. We always start with the one that we have a value, like a quantity for. And we want to know how much moles of water are produced if we have this many moles of oxygen. Well, we just take the coefficient that's kind of hidden there. We have a 1 mole of oxygen. And then we have 2 moles of water that can be produced from that. So it's very similar to the one above. Here I'm going to carry through with all my sig figs. Since there's 3 sig figs here to start with, I need to have 3 sig figs in my final answer. So 10.0 moles of water. Wonderful. Next problem. How many moles of SO2 are required to make 125 moles of CS2? All right, so this is, again, not balanced. So let's start by doing that. We have free carbon on the left side, so let's leave that one to the end. We have the wrong number of sulfurs, so let's go ahead and multiply the sulfur dioxide by 2 here. Now I've fixed the number of sulfurs at 2. The number of oxygens on the left side is 4. So let's make 4 carbon monoxides on the right. How many carbons do we have on the right? Well, we have 1 plus 4, or 5. So we can add a 5 right there. All right, so how many moles of sulfur dioxide are required? Well, let's start with this product here. So we're actually starting with the product this time. We have 125 moles of it. So this is our A on that chart up above. And we just need to look at the coefficients here. So there's a hidden 1 there. So 1 mole of CS2, carbon disulfide. And we can get 2 moles of sulfur dioxide. So we need 250 moles of sulfur dioxide for this reaction to occur. All right, next problem. If I have potassium chlorate, this is this compound KClO3. We'll learn how to name those later on. It can decompose or break apart into simpler substances of KCl and oxygen in the presence of this catalyst, this manganese oxide compound. So if we have 1.50 moles of it decomposing, and we want to know how many grams of oxygen are going to be produced, now we need to do a couple steps. So let's look at the flow chart. We're going to start with moles of A, and we want to find grams of B. All right, so in this one, we're starting with the potassium chlorate in moles. We want to find the moles of oxygen and then multiply by the molar mass of oxygen. .50 moles of KClO3. And now I haven't balanced it yet, so let's stop here and balance this reaction. Did I balance that one? Yeah, I did. Well, the only thing that's not correct is the number of oxygens. And so I have an odd number on the left and an even number on the right. Here's where I can make use of the least common multiple method. And that corrects the number of oxygens. And then I just need to fix the number of potassium and chlorine to 2 each. All right, so there we have it. So every 2 moles of KClO3 that decomposes can produce 3 moles of O2. And then what we need to do is multiply through by the molar mass of O2. So what's that? The molar mass of O2 is 16.00 times 2. So the mass of one oxygen atom times 2. We're not going to multiply it by the coefficient here. That's a common mistake. The coefficients don't affect the molar masses. All they affect is this stoichiometry component. All right, so that's already accounted for there. We don't want to double count it. So oxygen is the molecule is 32.00 grams per 1 mole of it. Let me write it out fully like this. Grams of O2 per 1 mole of O2. All right, before we do the calculation here, we can see that everything will cancel out except for grams of O2, which is what I was trying to solve for. So let's pull out our calculator, 1.5 times 3, and then I need to divide by 2 because it's on the bottom there, and then I need to multiply by 32 because it's on top. All right, I could also multiply everything that's on the top first and then divide by everything on the bottom. So we're going to get the same answer of 72. We actually have 3 sig figs we need to worry about. We have 1, 2, 3 here. We have 4 sig figs there. But let's go ahead and add our 3rd sig fig, 72.0 grams. And we want to always include the substance. So grams of O2. And I don't know if I had been doing that. I have been doing that. Okay. So you always want to include the substance in your answer. It helps tremendously. All right, here's another gram to mole problem. This might be a good one to pause the video and try this one on your own. Okay, so if you solve this, and you can jump ahead to to the answer and check your work, or you can work through this one with me. And so in this one we have magnesium metal being dissolved in hydrochloric acid, and we're going to get some hydrogen gas that evolves, and we're going to get magnesium chloride dissolved in the solution. So this AQ is a new state of matter I haven't talked about. It's called aqueous, and that's when you have something dissolved in water. So the HCl is dissolved in water, and this makes it an acid now. So it's not hydrogen chloride anymore, it's hydrochloric acid. We'll talk about that in chapter 10. So let's go ahead and fix the equation so it's balanced. We don't have the right number of chlorine, so we need 2 HCl molecules, and then that balances this equation correctly. If I have a small ribbon of magnesium, and this would be around 1.5 grams, and it reacts with excess HCl, it might be interesting to know how much hydrogen gas is evolved in the reaction. All right, so let's go ahead and start with the mass that's given. Now, before I can use the stoichiometry, I need to divide through by the molar mass of magnesium, and we can see that on the chart up above. So in this case here, we're going from grams of A to moles of B. So we need to divide by the molar mass of A. All right, so magnesium should be 24.31 grams per mole. And then we can use the stoichiometry here. So for every 1 mole of magnesium, we want to know about the hydrogen gas, so we can get 1 mole of hydrogen gas. Now here we're multiplying, dividing by 1, but it's still important that we write this out so that we can see how the units cancel properly. All right, so let's 1.5503 divided by 24.31. We don't need to worry about the ones here. That gives us 0.06377. We have 5 sig figs in our starting value, but we only have 4 sig figs in our molar mass. So I would only use 4 sig figs here, 0.06377. Okay. All right, so this is another problem here that is a decomposition of a material. In this one, we are starting with grams of a product, and we want to know the grams of a different product. So we're actually worrying about 2 products here. We're not dealing with anything on the left side of the reaction. This is an interesting example of stoichiometry. See, again, it doesn't have to start with the left and go to the right side. We can worry about just one side of the equation. But here we still need to balance it. The least common multiple method works the best here because the oxygens are odd and even. So there we go. And then I just need to make sure I have the right number of sodium chlorides. And we have our ratio of 3 to 2. So for every 3 moles of oxygen, we're going to have 2 moles of sodium chloride. Now, how many moles of oxygen do we have to begin with? That's the challenge, right? So we can't compare this directly. We have to go, in this instance, from grams of A all the way to grams of B. So here's where we have the most common calculation you're going to be doing with stoichiometry. We're going to divide through by the molar mass, multiply by B, divide by A, and then multiply by the molar mass of B. All right, so let's go ahead and do that. Let's practice it. So we're going to start with 80 grams of O2. And above the chemical formula is where I like to write out my molar masses. So we're going to need both of the molar masses here. So the molar mass of sodium chloride and the molar mass of oxygen. We already calculated oxygen above. It's 16 times 2, or 32.00. I'm only going to use 4 sig figs. For sodium chloride, sodium is 22.99 and chlorine is 35.45. And when we add those together, we're going to get the molar mass of sodium chloride is 58.44 grams per mole. All right, so let's start by converting the mass of oxygen to moles of oxygen. So we'll divide through by 32.00 grams oxygen per mole of oxygen. We'll look at the balanced equation now. So for every 3 moles of oxygen, we'll get 2 moles of sodium chloride. And now we can see here that we need to multiply through by the molar mass because it's grams per mole. So if I want to find grams, this has to be on top. All right, what do we get? So I always like to do things left to right. So if I have a problem like this, I'm going to do 80 divided by 32. And then I'll multiply by the fraction 2 divided by 3. And then times 58.4. 97.4 grams of sodium chloride. All right, we got 2 more problems left here. Last one here. What mass of NO, or nitric oxide, is produced by the reaction of 6.4 grams of oxygen gas? So what mass, that could be grams or kilograms. We're just going to say grams here. So this is another gram to gram calculation. Let's start by balancing the reaction. The nitrogens are balanced, the hydrogens are not, the oxygens are. But let's start by balancing the hydrogens. So we'll do least common multiple, 3 and 2. Then we'll fix the number of nitrogens. So there should be 2 here. And then we can look at our number of oxygens. Well, there are 5 on the right side and 2 on the left side. So here we have a 5 halves situation. Now here, we can leave the problem as a fraction. That's not going to be an issue. 5 halves is the same as 2.5. We can do this problem with 2.5 as a way to do this, but I'm going to go through and I'm going to multiply everything through by 2, just because it does create some issues otherwise. So let's fix that. All right, so this needs to be 4. This one needs to be 5, 4, and 6. All right, so I balance equations fairly quickly. It's going to take you a little bit of time to learn how to do this. I just have had a lot of practice over the years. So what mass of NO is produced by the reaction of 6.4 grams of oxygen? Well, here we're going to start by doing the conversion from grams to moles so we can compare these molecules. That requires us to divide through by the molar mass, which is calculated above. Okay, NO, that's also on the right side of the reaction. That's my brother. He's playing some video games. Let's see here. So 6. Oh, okay. No, yeah. So we're starting with oxygen on the left side. So oxygen is 5 moles of O2, 4 moles of NO, and then we need to know what the molar mass of NO is. So let's calculate that. It's 14.01 plus 16 or 28 point, not 28, that's 30.01. So 30.01 grams of NO per mole of NO. .8016. So I'm going to round it to 3 sig figs. So 4.80. And your answer, if you're starting with grams, and you're ending in grams, your answer and your starting number should be in a similar range, right? So we go from 6.4 to 4.8. That makes sense because we have 5 moles of O2 reacting, and we only get 4 moles of NO. So this number should decrease slightly. Oh, and the relative molar masses of these two are similar. All right, so this last one here is an interesting problem where we can actually determine how many molecules of water there are. And let's look at how this is. So we have how many grams of hydrogen are required to produce 1.23 times 10 to the 24 molecules of water. All right, so we're starting here with grams of A, so grams of hydrogen, and we want to find molecules or particles. You can think of particles of water, which is B here. So we're going to start by dividing by the molar mass of hydrogen, using the balanced equation, and then multiplying through by Avogadro's number, that conversion factor that we learned at the beginning. We want to balance this reaction before we begin. The oxygen is not balanced, so I'm going to put 2 here and then a 2 here. What's the molar mass of hydrogen and the molar mass of water? Well, we're not going to need to know the molar mass of water here, actually. But let's find it for hydrogen. It's 1.008 grams per mole times 2, which is 2.016. So we'll need that. But we need to start with the molecules here. Actually, I did this backwards. Let me fix that. I'm sorry. That's why you have to read the problem correctly. Particles of A to grams of B. So we're going to go the opposite direction. And if you don't know where to start, try canceling out your units. That is going to be the key here. All right, so here we have molecules of water. Well, according to my chart there, it said we need to divide by Avogadro's number, right? So 6.022 times 10 to the 23rd molecules of H2O per mole of H2O. Okay, there we go. So we divide those two. Then we get moles of water. Then we can use our balanced equation. So for every 2 moles of water, and we don't want to put 2 over here, just over here, 2 moles of water, we can get 2 moles of H2. 2 moles of H2 are required. Then how many grams of H2 are required? Well, here we need to multiply through by the molar mass. So 2.016 grams of H2 per mole of H2. So here you want to make sure you're using the E key on your calculator, or you're using parentheses. Otherwise, you're going to get the wrong answer here. Now I can multiply through by 2 and divide by 2, but I know that's going to cancel each other out, so I'm just going to ignore that step there. And we get our answer is 4.118. 4.118. We want to use 4 sig figs. It's always good to box your answer on a test, so I know what your final answer is, unless I have a spot for you to put it in. All right, so I would make sure you get a head start on some of this material. This homework can take some time to do. On the upcoming midterm, I'll be asking some problems of this sort, so make sure you take a look at our practice exam and let me know if you have any questions. Take care, and I look forward to our lessons next week.